uh, our solar system. This is just a concept, an artist's concept of how our solar system will look like if you see it from far. So on in the center of this disk is the sun, and that's where our solar system is as a disk. Around us, around it, very far away, about up to 150 angstrom unit. 1 angstrom unit is the distance between Earth and Sun. If you go very far away, up to 100 and beyond, you start seeing this uh, population of icy objects in what we call the Oort cloud. This is the Oort, the scientist who hypothesized that such a cloud exists very far away from the sun, and that's where all these icy bodies are. As you go away, the disk becomes more like a, so this is three-dimensional. It's like a cloud of icy particles in the outer edge of the solar system, and it's from here that the comets come visiting us uh, close to Earth, and that's when we see it. This is the case of our solar system comets. And you would have heard of periodic comets that visit us, like the Halley's comet comes in once in 76 years. So when comets arrive into the inner solar system, what we are interested in studying is about its structure, what is it made of, its period, uh, and particularly for Earth and the Moon. This is a very interesting area because one of the mysteries that we have on Earth, for example, is how did we get water on Earth? Now, water is something that we take for granted, use every day, but still we do not know really how did so much water come on Earth. Why is that? Because early solar system, according to what we understand about how solar system formed, the temperature here in the inner solar system was so high that you cannot condense molecules like water. No, when you have above 100 degrees Celsius at atmospheric pressure, water evaporates into its vapor phase and it's lost. So at those early times when the Earth and the inner planets formed, it was so hot here that you could not have condensed water. So how did then all the water on Earth specifically came from? So we believe partly it must be from comets, and comets deliver water to Earth. This is just an hypothesis. We have not been able to completely prove it, but studying the composition of comets is therefore very important for us because possibly this is what brought water to Earth, and there is possibility that even life on Earth, because that's again one of the most important questions that we are seeking, like how did life emerge on Earth? Only Earth, right, in the solar system. So comets are therefore very important because they can tell us about not only what happens in the outer solar system, but how things on Earth changed because comets came in. There are regular comets and interstellar comets. We're getting excited about Atlas, 3I Atlas, because that's an interstellar comet. Regular comets are the ones that are born in our solar system, as I showed in those outer regions. They follow elliptical orbits around the sun, so they return periodically. Sometimes you see it only once in a lifetime because it has such a long period, so you may not see it in one lifetime. But sometimes it returns periodically. Halley's comet every 76 years, and they are hypervelocity objects, typically like 10 to 70 kilometer per second. Um, and interstellar comets, we have had 3 visitors so far. How do you recognize them? They come from other systems. So they were born around some other star and happen to pass by, and we are seeing them. How do we know they are from different star? By following their trajectory. Like if you look at their orbit and calculate from where did they start, so you can retrace that path back, right? Like if you have studied about ellipses or conic sections in school and college, you will know that if you know the eccentricity of an orbit, you can calculate other parameters. Looking at the angle, etc., you can trace back where is the origin of that. So we find that they are in hyperbolic orbits, which means they're not closed orbits. And if you trace back, you can sort of estimate from where it came from, and we understand that this therefore that they have not originated in our solar system, and they typically travel at extremely high velocities, above 60 kilometers per second. This is also another clue because You need such hypervelocity to escape the gravitational field of their solar system and be thrown out. And we cannot today send spacecrafts to other solar systems, right? We can study our own solar system by, I mean, there are even probes that's been sent to Pluto, and the Voyager spacecrafts have reached the end of the solar system. But in our lifetimes, at least now, we don't have the technology to send spacecrafts to other star systems. But now this is a free source that we have. These comets are coming from other systems. So they tell us about how they formed, and uh, are those systems typical like ours. 3i Atlas was discovered very recently in July. You can see the image of discovery from the Atlas telescope. The orange mark there shows the comet moving. This is a telescope in Chile called Asteroid Terrestrial Impact Last Alert System. So it is basically made to alert if there are asteroid impacts, which means it is tuned to look at fast moving objects by taking snapshots of the sky. So you keep looking at the sky, take many photographs, and you can identify. No, you can code and make softwares to identify what's changing between the frames, so they can automatically identify. So this is how Atlas 3i Atlas was identified. The 3i there just means the third interstellar object. Uh, it was about 4.5 AU from the sun when discovered, and its velocity was estimated by tracking it. It's about 1 to 2 kilometer in size. So it's pretty small, and it's only the third visitor. And on the down there, the blue is the Hubble Space Telescope image of the 3i Atlas. All the big observatories out there in the space are pointing towards it. So we have several images of them. This shows the how the comet is moving. You can see the imaginary orbits of Jupiter and other planets, and you can see how 3i Atlas is moving with respect to that. So can you see that these are hyperbolic orbits? So now if you trace them, you can complete its trajectory and find out more about the origin of this. All observatories, as I said, are looking at this object. On the left upper part, the colored image is from the largest optical telescope that we have in space, the James Webb Telescope. It's a 6.5 meter, the largest ever telescope up there, which can resolve this very well. You can see the central bright region, the orange gas around it. This is a false color, basically depicting what it is made of. So from this, we understand this is mostly carbon dioxide, and the very faint glow around it. Down is a picture from ExoMars, which is on Mars. So from there, they have imaged it. And on the top right is from our own telescope. So do you all know which is the largest telescope we have in India? There is a ARIS. There is a 3.6 meter in Nainital. This one is from the Hanle. So in Ladakh, there is a Himalayan Chandra telescope. Uh, the image that you see on the top right is taken from Hanle. So we have good telescopes in India too to look at this, and they are indeed pointing at that. There were two before this. There were two more such interstellar comets. Uh, Oumuamua, which is a very cute name, I guess. It's cigar shaped. What you see here is just an artist's drawing, but it's like no visible tail, and the shape is very odd. It's only about 100-meter long, so it's very very small. Then Borisov in 2019, a very clear cometary activity was seen, and very carbon CO rich composition. And the third one is our 3i Atlas that's currently there. That also has an unusually rich CO2 composition. So the composition tells us how it formed and from where exactly it must have come from, which stellar systems. How do they come? Obviously, it's born in another solar system, forms around a distant star, just like our comet, and it's somehow got ejected from that system. Could be gravitational interaction with the giant planets. Uh, Suppose it's there is some perturbation that nudges it out with this high velocity. That's how it must have come. probable that in our own solar system too, the very edge comets could just get flung out of our system. It travels for millions of years, so it might lose some of its material, drifts through the galaxy where the temperature is very cold. It could accrete other chemical substances as it travels through the galaxy. And it's a chance encounter with our solar system. So we just turned lucky that in our lifetime, AI athletes happen to pass by and is caught by the gravitational field of our solar system and is now passing through. And once it leaves, it will not come back because it's not a periodic phenomenon, right? It's just a chance event. We have now very good orbital details. It's not bound. The eccentricity is much high, 6. For comparison, Earth's eccentricity is 0.017, so it's an ellipse. Halley's comet is 0.967, so it's still bound. Velocity, as I said, is very high, and the escape velocity from the surface is only 20 kilometer per second. So, what is the importance of escape velocity? Escape velocity of a molecule is what it keeps it on the surface bound to a planet. So, on Moon it's about a few kilometer per second. So it just says that can it hold on to light molecules? It's closest to the sun, probably yesterday and this time scale, and this is when it becomes most active. But because it's close to the sun, we can't observe it with currently from India from the telescope. When it comes out of this, we can again see it, and it is rotating. So once in 16 hours. So all of these objects are spinning. Even our own asteroids and comets are spinning. It could be original spin, or it could be, as it passes through the galaxy, getting a gravitational nudge and spinning makes or a collision that makes it spin faster. Spectroscopy is what tells us what it is made of. So you can see here, for example, on the right down from JWST, a spectrum. So a spectrum basically gives you, as a function of wavelength, the intensity. So at every wavelength, what do you see? So can you see those emission lines? Those peaks there are carbon dioxide lines. And that's how we estimate how much of carbon. The stronger those lines are, more that molecule is present there. On the top is an image from JWST. So from every pixel of that, you can get a spectrum. And that's how we estimate. So you estimate that the CO2 to H2O ratio is like 8:1. And most solar system comets are water rich dominant. So here there is a exception that this is more of carbon dioxide. It's reddish color, it's a false color. It's coming from the slope. You can see those 400 to 700 nanometer. There is a slope. So the steeper it is, more redder it will be, which indicates it is organic rich materials. Uh, there is gas production there, and it is losing mass 0.3 to 4 kg per second. Because as you follow this, you can see how it's getting lost and shows unexpected activity levels. There are large dust grains, not visible in the tail initially, but subsequently, when it comes closer to the sun, we're able to see it, and an asymmetric coma, which means that the circle around it is not symmetric. So it indicates its irregularity in shape. As we spoke about it, why are they so important? Because they are windows to other worlds, direct samples from alien planetary systems, understanding planet formation, searching for building blocks of life, galactic population studies, how many planetesimals are out there, understanding planetary system dynamics. Each discovery is precious because we have so very few of them. Can we see Atlas with your backyard telescope? Unfortunately, no, because this is very small, it's very faint. The magnitude. So, magnitude is what we use, the term that we use to look at the brightness of an object in the sky. The estimated magnitude is like 15 or 16, which is very faint. The smaller the number, brighter is the object. Even at the closest, the magnitude would be 12. So that's very, very low. We can't see it with the naked eye. Our limit is 6. And if you have a binoculars, that is about 10, and a small telescope, 14. So you can't see this with a backyard telescope. You at least need probably a 10-inch telescope to try and see it, very dark location. And it's moving very fast, so you will have to track it. Um, if you really want to try, you have to look at pretty big telescope, have a really good tracking mount, and a dark sky sight. And the ephemeris is available online, so you can look at that. What's happening now? July 1st, we discovered it, and Hanley had a observation at July 3, which is the HCT. So if you haven't visited HCT, it's a good time to go there. Um, and there was an intensive observation campaign with all multiple telescopes looking at it in various ways: spectroscopy, photometry, imaging. So photometry means you just collect the light. Spectroscopy means you disperse the light into different wavelengths and look at it. November onwards, it's moving away from the sun, will become fainter, and eventually won't be able to see. So there is a very small time window. It's unique, it's largest, biggest interstellar object detected. It's the fastest, most CO2 rich, possibly the oldest interstellar object. Has been traveling for a long time. Most active, shows unexpected dust production, and we still don't know. We need answers to a lot of questions. Where did it come from? Which star ejected it? Why such unusual composition? How old is it? Will it survive even when it goes close to the sun? It could break up. What can it tell us about alien planetary systems? How many are there? Based on 3 detections in 8 years, if you just do a probability calculation, there should be trillions of them in our galaxy. But the detection challenge is that they must pass close enough to Earth, must be bright enough. You should be able to see it from the inner solar system, and the window of opportunity is very small. Bigger telescopes will in future help us probably track more of these key takeaways. So that's my last slide. Comets are icy remnants, very, very important objects because these are ancient. These are like fossils that you dig up from the past. Tells us the conditions that were there in the early solar system. And you can't really go and get these samples like from moon. We go and get samples from the moon, but these are so far away we can never do that. But they are coming to us, so that's a very important opportunity. And 3i Atlas is only the third such interstellar visitor. Currently, all Indian observatories and worldwide, there is a campaign to observe it. And studying them helps us understand about the larger scale of things in our universe. Thank you. That's all I had. I'll take when if you have questions, I would be happy to answer.
Thank you, ma'am, for your wonderful lecture. Now we'll have a small Q&A session. Students are free to
Sure.
ask questions. Yes. Do you have a question? Yes.
আচ্ছা বাংলায় বলবো না ইংরেজিতে ম্যাম হাউ দ্য টেলস অফ দ্য কমেটস আর ফর্মড
Yeah, that's a good question. So when it comes closer, the phase that is facing the sun heats up. So this is basically there are two things. There's dust and there is plasma. So there is solar wind also from the sun. So that pushes it in the opposite direction, and so that it starts forming a tail. So see, Earth also has a magneto tail, for example, which is coming due to the solar wind pressure. So when it comes closer, you will start seeing this tail. Basically, it's plasma pushed away by the solar wind.
Okay.
Is
Now
that
next question.
Ma'am, basically, I have two questions to ask.
yes?
So, first one, recently in China, 5 suns have been seen, and recently in India also red moon occurred. So, why this event happens? Means, is it a special solar event?
No. In China, what did you say?
Like recently, 5 suns were occurred in the sky.
5 suns won't occur. That must be some wrong thing that you have read. Can't, no? We have only one sun, right?
Yeah, but the red moon.
Yeah, red moon is just a like when you see it in the low in the horizon, how does the sun redden? Same way, atmospheric refraction. So it's just a refraction in the atmosphere. So when it comes through the atmosphere, it reddens. So it's just an atmospheric phenomenon.
Okay, one more question.
Ma'am, these kind of interstellar comets are being seen in the present days. In past, where there are no interstellar comets, or we didn't had the technology to discover it.
Yeah, we didn't have, right? So they must have come in the past too. But see, now we are discovering it because of big telescopes. So many of them are too faint for the eye. You see, so you can't see them. So yes, past also must have come. We haven't been able to see it.
Any more questions? Yes, to me. Yes.
Ma'am, my question is how the interstellar comets are giving information about the other star systems.
Yeah. So that's what I said. Like when you, if you look at their composition, uh, I mean, these are formed in other solar systems, right? Like in our solar system, we know where it is coming from because of its composition. Because it's made of ice, it cannot be from the inner solar system where it's very hot. Things were very hot in the beginning. So we assume that this formed in the outer solar system. So it has the composition of the initial solar nebula, what the conditions were in the nebula from which it formed. Now, if we look at interstellar cometary composition, it's showing us a different composition, which means the host conditions, the original composition of that stellar nebula and pressure, temperature, how it varied at that time determines its composition. So you can work back, no? Now, if you find the composition of this, that should tell us how it formed. So that way.
Okay.
Is that clear? Yeah.
Yes, ma'am.
Yeah.
Ma'am, I am asking that we are getting this kind of information. So what is the need
Oh.
of this information? Is it helping us?
Yeah. So as I said, no, do you know, like let's say how Earth got its water? Hmm? We don't know yet. It's possibly a part of it came from comets. These are things that ask us it's not a like a direct societal application or a technology thing. These are basic questions that help us understand very profoundly how did life begin, how did earth came, and why are planets habitable. Isn't that a miracle that only earth we know that life is harbored. Now, are there such systems outside? Finding water in other systems help us understand that there are other stellar systems with water, which means there should be life elsewhere as well, right? So, these are things that are basic to understand our own existence on Earth. So we can take it that way.
Thank you.
Ma'am, I have a question that you said that because of the gravitational field of the planets, the comets are getting attracted and we can see the comets. So
Yeah.
so from this information, can we get the range of the gravitational field from the planets?
Yes, but that we don't need this comet. I mean, I understand what you mean. Like if you look at the trajectory of the comet, uh, we can see how much it is getting pulled by each planet. That's what you mean, right? Yeah. Is that what you mean?
Yes, yes.
Yeah, that's correct. But okay, but to understand our own gravitational field, we have other ways of doing it. So we don't have to wait for this comet. It's sort of the other way that we are now trying to do it, knowing that how much Earth's gravity, or when it passes through near each planet, we know how much it is going to get pulled. So we can look at its trajectory properly. But you're right that either way works. Like if you want to study, you assume its trajectory and then study how does the our gravitational field affects it. That also possible. Okay.
Ma'am, I have a question that
Yeah.
why only Atlas rotating around the sun, not around the moon or the earth?
It couldn't pull it enough. So it's coming at a very high speed. sun's gravity is the most high now here. So if if it's coming very close to Earth and Earth can pull it towards it, it will come and orbit around Earth. But currently it is too small. So you know the gravitational force between two bodies depends on the mass of both the bodies, right? So in solar system now, that is such a small body. So sun's gravity is the most dominant force here. Therefore, it is pulling it towards it.
Okay, we will take two more questions only.
Yeah.
Ma'am, you mentioned that the pictures you have shown us are false color. Then how we conclude that which gases they are composed of?
So that's a very nice question. So color is here, we are only representing, but the line is correct. Like, so if you say CO2, we precisely know which wavelength does the CO2 emission come from. When I meant false color is that, see, now here we know that if you take a certain gas, what is its color? But this is not really representing that color. CO2 is colorless. So here they only, color it to show how intense it is. So it is not from the color that we make out it is carbon dioxide. It is from the spectrum, which means at each wavelength, how many photons you get. And you see that at the wavelength of carbon dioxide, you get a very strong peak from the spectrum, which means there is a lot of carbon dioxide in the coma. Okay, so it's from the spectrum you get it. Then you're just representing it as a color. Like when you draw a picture, you do different shades to get the contrast. That is being done. That's all.
Okay, last questions.
So, ma'am, as we know that there are many universes, so is there any planet like Earth which exists in the other universe?
We don't know yet whether there are different universes. Okay, there are theories of parallel universes, but yeah, it's all more theoretical. But coming back to your main question, there are trillions of galaxies, trillions of stars, which means so many more planets like Earth around sun-like stars. We don't have any proof for alien life yet, but if you just do a probability calculation, then very likely that there should be life elsewhere, because we don't see anything special about our Earth and our sun. It's very ordinary planet and very ordinary star. Just so happens that we have life here, so it can't be like in the whole of universe and trillions of objects only Earth has a life. So it's only basis of such probability arguments that today we can say there must be life elsewhere. We have now 6,028 exoplanets discovered in our galaxy, which means planets around other stars. And if you look at their atmosphere, we find signatures of water, carbon dioxide, etc. But so with an indication that probably these planets could harbor life. But it's very, very imaginative at the moment. But if you ask me, most likely there must be life. May not be like us, but
No, no. Remember, last question.
yeah,
Very
sure.
much interested. Okay.
Yeah.
So, ma'am, can we determine the mass of the comet by the information that it gives?
Yeah. So how do you? So just somebody else now asked about the gravitational field, right? So you know the formula Vm1 by m2 by r square, right? So if the comet is passing in the gravitational field of another object like Jupiter, or just take the sun, how much it is getting pulled will depend on its mass too, no? The gravitational force between them. So looking at its orbit, we can calculate the mass. So yes, you can.
Okay. Thank you, ma'am, for your precious time, and we all have a wonderful session, and we have learned many things from you. Thank you once again for being with us.
Thank you. Thank you
ma'am.
for asking all those questions. It was very nice. Thank you.
Thank you,
Bye.
ma'am.
হ্যালো
এটা কেটে দিই। লাইভ
স্টুডেন্ট যারা আছো একটু ওয়েট করো আমরা